Okay, so now that we know how to draw Lewis dot structures of molecules, we can now use those drawings to figure out some properties. And to be able to figure out properties, we have to know the shapes of these molecules. Now, what is a little difficult is that you're going to be drawing these on a piece of paper, so it's 2 dimensions, but these are not 2-dimensional things. These are 3-dimensional things. So you're going to have to kind of use a little imagination and be able to rotate this piece of paper drawing 3-dimensionally. Now, in class last year, you may have used molecule kits, and we can still use some molecule kits, but when it comes to testing and lots of other things we might do, you're not going to always have these test kits with you to be able to manipulate and look at these things 3-dimensionally. So again, a little imagination to be able to do this 2-dimensionally and kind of render it into a 3-dimension. So we'll get a lot of some vocabulary here, and there's not a ton of memorization in this class, but definitely this section, Unit 2.7, there are some things that you're going to have to memorize for this. Okay, so we're going to talk about VSEPR. I know it's not going to kind of pronounce like it's spelled right there, but a lot of people call this Vesper. And this is going to give us some ideas about how to come up with the shapes of these molecules. And we're also going to talk about hybridization, whatever, we don't know what that means yet. So last year you did talk about Vesper. And where does all that come from? Valence, shell, electron, pair, repulsion, and using a, like we've drawn water before. Here is water, and you could draw this probably a number of different ways. Let me erase that little dot there. Again, I said that it's nice, not always, you don't have to, but it's nice to circle those unshared electrons. And a line represents 2 electrons that are being shared. So now there are 4 pairs of electrons that are all repelling each other. So those are electron pair repulsions. And those will now give that molecule a certain shape. Okay? This is important. The lone pairs. So here's a lone pair, and there's a lone pair. They have more ability to repel than the paired electrons do. So there won't be an equal repulsion between all 4 of those sets of electrons. The 2 that I check marked repel a little bit more. Okay, so here are your shapes that you will have to know for this class. Linear, I think, is pretty easy. You could have it obviously with 2 atoms. So here is hydrogen, and here's fluorine. This is the Lewis dot structure for those 2. So anytime you have 2 atoms, you're going to have linear. I think that's going to be pretty easy. The bond angle, you don't really have a particular bond angle when you only have 2 atoms, but we'll still consider that 180. Carbon dioxide, on the other hand, has 3 atoms, and it has a true 180 bond angle there. And when we talk about the bond angle, we're always kind of considering well, in this case, 3 atoms, it's going to consider everything. But we're always going to consider that middle, that central atom. Okay, and also, if we're only talking about these geometries, you could just get away with drawing that as long as you know that those other electrons are residing in the oxygens. Or if the question on a test says draw the complete Lewis dot structure, then you got to make sure you draw all those dots. You didn't have this one, I don't believe, last year. Trigonal planar. And BF3 is a nice molecule for that one. I don't know if you remember, but boron is an incomplete octet. It does not have 8 electrons around it. So boron, its outer electrons plus fluorine's outer electrons is going to give you a shape that looks like this. And again, I didn't draw all the dots around the outer of fluorines because that's not going to have anything to do with its shape. But if you can kind of think about this as a circle, here I'll draw a circle over here, and kind of cut into 3 pie pieces. Each of those is going to have a bond angle of 120. Bent. And by the way, there's multiples of these linears or trigonal planars or bents. But here would be a bent molecule, sulfur dioxide. And you don't have to draw these at these angles that I'm drawing them, but it kind of gives you a better indication of why that it is bent. Okay, so sulfur's outer electrons plus oxygen's outer electrons will give you that. And actually, that's a resonance structure. You have a single bond and a double bond. That double bond and single bond can switch spots. And then we have these 2 electrons right here, which is going to be extremely important. Those 2 electrons are going to repel the electrons between the sulfurs and the oxygen, the sulfur and the oxygens. And that's going to give this bond angle right here. Not a very good arrow there. Let's just erase that arrow. But that bond angle right there is going to be not the linear that we had before. It's going to be less than 180. And if you look here, we're going to talk a lot more about this. It actually is not that much different between the trigonal planar. Trigonal planar has 1, 2, 3 spots that electrons are coming off the central atom. We call those spots domains. The sulfur has, let's go with a little different color here. It has 1, 2, 3 spots that electrons are coming off the central atom. It's just that in this one, they're all bonded. And in this one of them are not bonded. And remember that the unbonded electrons repel a little bit more. So instead of being 120, we don't know exactly, because you would have to get in there with some spectroscopy to figure this out. But it's going to be a little bit less than 120. And if it was different atoms, not sulfur and oxygen, it might be even a little bit different than 120. And again, you wouldn't know that unless you experimentally figured it out. Okay, you talked about tetrahedral, and it's kind of strange. I have here tetrahedral family. Well, you could actually have tetrahedral, and that has 4 actual bonds coming off the central atom. You could still have 4 domains, but one of them not be bonded. So it's still in the family of tetrahedral, but it's not tetrahedral as far as molecularly. It's trigonal pyramidal. And I think you had to memorize that one last year. And I don't know if you had to memorize the bond angles, but this year there's a few bond angles you have to know. So tetrahedral, certainly, by the way, 2-dimensionally, those bond angles look like they should be 90, 90, 90, 90. But remember, this is not 2 dimensions, this is 3 dimensions. So in 3 dimensions, they can get further away from each other than 90 degrees and 109.5. Trigonal pyramidal, because these electrons repel a little bit more than the other ones, it's going to have to be a little bit smaller than 109.5. In this case, for ammonia, 107. And then water, still has 4 domains of electrons, but 2 of them aren't bonded. So those 2 can repel even a little bit more. In this case, 104.5. So if you know those 3, that's going to get you very far. Okay, so now these are expanded octets. We talked a little bit about that the other day. And this family is called trigonal bipyramidal. That's brand new for you. I definitely you have never seen that before. And let's do trigonal bipyramidal, the actual molecular shape. And it's going to look a little crazy. And it has 5 bonded pairs. And it's going to be a little difficult to kind of visualize this 2-dimensionally. But there are angles of 120 and there's angles of 90. In class, I'll get my molecule kit out and I'll show that to you. You could probably find this a 3-dimensional image on Google also if you don't want to wait, and you can take a look at how that can rotate, and you can see the 90s and the 120s. If one of these domains is not bonded, like in this molecule, you would have, whoops, that's carbon, we don't want carbon, sulfur, with 4 fluorines. That molecule has these 2 electrons that are going to repel a little bit more than the bonded ones above. So instead of 90 and 120, they will be a little bit less than 90 and a little bit less than 120. It is not going to be important to know those numbers because you'd have to do, again, the spectroscopy to know the exact angles, but it's going to be a little less than 90 and a little less than 120. Okay, and you can get really impressive with your vocabulary here by calling it distorted tetrahedron, but a lot of people call it seesaw. And once I show this to you 3-dimensionally, or if you Google it 3-dimensionally, you can see that it actually looks like a seesaw. And it can kind of rotate on its axis like a seesaw can in a a playground. T-shaped, has 2 pairs that are not bonded, and then, whoops, that's a fluorine, and 3 that are bonded. So that's going to even bend it a little bit to a smaller angle. So we started off with 90. This one was a little less than 90. This one's even going to be even a little less than 90. And then I3 minus is going to give you this look. And remember brackets if we have a polyatomic ion. And this is going to be, again, difficult to kind of visualize 2-dimensionally, but 3-dimensionally, these do repel more than the bonded ones, but they are going to be in a situation where they're going to be repelling equally. So it actually is going to give it a linear look. And again, when I get my molecule kit out in class, you'll be able to visualize that better. And again, if you can't wait, if you Google, you'll be able to see a 3-dimensional representation of that. I'm sure you can find one there. Okay, and our last family that we're going to discuss is octahedral. And octahedral has 6 domains. So sulfur hexafluoride is a good example. And you're going to say, wait a minute, how is it oct, the prefix oct, when it only has 6 things? Well, the octahedral comes from how many facets, how many sides to the molecule. And if you actually were able to look at this 3-dimensionally, you could kind of visualize it. It would actually have 8 particular sides to it. So that's how someone way before me coined this octahedral. And if they're all bonded, then you got perfect 90s. And then as you have less domains that are bonded and more that are unbonded, lone pairs, then those angles are going to get a little bit less than 90, typically. Square pyramidal. So that's actually a misprint. I don't know why that says that there, but okay, and that one is going to look like that. Yeah, these are all fluorines. So these 2 electrons right here are going to repel a little bit more. So instead of 90 between all the angles, it's going to be a little, between all the atoms, it's going to be a little less than 90. You can get a couple situations like this one. These all kind of, these repel each other equally. So actually you're back to 90 again. These are going to be perfect 90-degree angles with that one. Again, difficult to see this 2-dimensionally, much easier to see it 3-dimensionally. Okay, so let's draw a few of these. I'm probably only going to draw maybe 1 or 2 per slide, and then you guys can practice. Now, I doubt that you've ever drawn a molecule with that particular atom. But if you know other atoms from its column, it's going to have exactly the same properties as far as shape. I shouldn't say properties. It's going to have the same shape. So what else is in its column? Oh, nitrogen. It's a terrible N there. Nitrogen is also in the same column. So it's going to be just like NH3. So here's NH3. So guess what? AS is going to be same thing. So predict the geometry. This is trigonal pyramidal. And its bond angle is 107.5 if it was NH3. So it's going to be very close to 107.5. No, 107. I don't know why I said 107.5. So 107. Now, do I know specifically with arsenic? No, I don't. But it's going to be very similar to my 107. Let's do one more. OF2. Well, F is going to have the same, I know it's not in the same column as hydrogen, but remember that hydrogen kind of sort of goes in column 1, but it also sort of goes in column 7. So it's actually going to have the exact same look as water. Okay, so it's going to have, it's going to be a bent molecule. These electrons are going to repel more than the others, and it's going to have a bond angle similar to water. Water is specific 104.5 because it's fluorine, probably not exactly 104.5, but very, very close. Okay, so let's do a couple of these. I think we've actually already done I3 minus, so we're not going to do that one again. Let's do H3O positive, hydronium. So oxygen central atom. You know what? Let's actually go way back and let's try to figure out how many electrons how many dots we're gonna use. 3 for hydrogens, 6 for oxygen, and then that's a +1 ion, so we have to subtract 1 electron. So I think we're gonna have 8 electrons. So there's my 8 electrons. There's a hydrogen, and there's a hydrogen. Brackets, remember? So it's in the family of tetrahedral because it has 4 sets of electrons coming off the central atom, 4 domains, but one is unbonded. So it's going to give you a trigonal pyramidal and somewhere in the ballpark of 107. Let's do this one. C2H4. Now you may have memorized from organic that this is an ene because of that. Enes mean double bonds. 2 carbons, ethene. You don't have to know that for this. And this is a little tricky for geometries here. Probably hard to describe the overall molecule there. But let's take a look at what's going on with that carbon. By the way, the other carbon would have the exact same situation. How many domains coming off that carbon? It looks like we have 3, and the other one has 3. So we could look at the bond angles. And when you have 3 domains, that's just like BF3 maybe. And I don't know why I put 10 there. It has a bond angle of 120 if we were going to look at like the hydrogen to the carbon to the hydrogen, or the hydrogen to the carbon to the carbon. Bond angle of 120. Okay, so these ones look a little trickier. So maybe we'll try to tackle one of these. Let's look at, let's try that one. By the way, the atom that you have lesser of is always the central atom. So we got I. Obviously, we're going to have 2 F's here. Obviously, we're going to have brackets with a positive there. So we know that. Let's try to figure out what we have for dots. So they're all halogens, 7th column. So we have 3 of them. That should have 20, but we have a plus ion there. So that means we've lost an electron. So I'm sorry, 20 is going to be our final answer, but iodine is 7. Each fluorine is 7. So that's 21 minus 1 is 20 electrons. So we're allowed 20 dots. So what I suggest is that you fill them all up. And you don't need all those dots unless it tells you you need to draw the the complete Lewis dot structure. Okay, so let's put all those in. And what kind of number do we come up with here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There we go, 20. And it looks like we have a really similar molecule to water. So it's going to give you bond angles in the ballpark of 104.5. Because they're not the same atoms as water, it's not going to be identical. But there again, no way you could do that to know exactly unless you do the spectroscopy. But that would be our prediction. And you can do these other 2 here. So once you know the drawings, we can attach the dipole moment to this, and we talked about dipoles in a previous section. And if you have a situation where you have, in this case, water, a partial negative, and hydrogen's partial positive, it kind of has the look of a magnet, and you have a dipole moment. And if you have a dipole moment, it can attract and repel other molecules. So all we're going to try to do is look at the molecule, and if it's asymmetrical, water has an asymmetry to it. If you kind of rotate it around, it has maybe, in this case, a top and a bottom, unique looks. If you would rotate this molecule around, always it's going to have the same look. It has a middle that's positive, partial positive, and outsides that are partial negative. It is a symmetrical molecule. It doesn't have two unique poles. It has an inside and an outside that are different, but you need one side somewhere in the molecule to be partially positive, somewhere in the molecule to be other spot to be partially negative, and you'd have a dipole moment there. But so we're looking to see which ones are symmetrical and which ones are asymmetrical. If you have two atoms, you're definitely going to have one side that's partially positive, one side that's partially negative, if they're different atoms. Remember that you can figure this out by the general trend for electronegativity as you go from bottom left to top right. You become more electronegative. Those atoms become more electronegative. So fluorine is going to attract electrons more. Hydrogens are going to attract electrons less. So that has a dipole moment. Carbon dioxide, we've already done this one. This is a symmetrical molecule, no dipole moment. This is a bent molecule. Bent molecules have a dipole moment. They have an asymmetry to them. BF3 is symmetrical, so no matter how you rotate that molecule, it's going to look the same. So if it has symmetry, it does not have a dipole moment. Sulfur dioxide is interesting. Again, that's not the complete Lewis dot structure. That's not what the question was asking. The question was, does this have a dipole moment? And that unbonded pair of electrons is going to give it a look like that. So that is asymmetry. It has a dipole moment. The dipole moment would be sulfur is less electronegative, so it's going to be partially positive. And it's a little better if I would have drawn it like this to kind of signify, to show you that it has a dipole moment. Two-dimensionally. Okay, and then the last section here is a little bit of vocab that the AP folks want you to know. And the reason they throw this in here is because it gives you a better method to kind of look at those bond angles that we were trying to do with some of the, I think we did it with did we do it with, yeah, we did it with that molecule, and we were trying to figure out those bond angles. So something called hybridization, and hybridization deals with the outer valence shell, the S's and P's, and we're not going to get in any more detail than that If you want more information about valence bond theory, you could on your own look in the textbook and kind of visit that on your own, but none of it will be on in the AP Chem curriculum other than this SP, SP2, and SP3, so we better revisit that at least. So if you have one, and it doesn't really matter what these are bonded with, these are with hydrogens, but if you have 1, 2, 3 domains of electrons, it doesn't matter if they're single, double, or triple bonded. If you have 3 domains, you have something called sp2 hybridization, and that is going to give you, and we already mentioned this in that previous slide, gave you a bond angle of 120. sp3, a good example of that would be methane. It has 4 domains, 4 orbitals coming off the central atom. So those are always going to give you, I know I have 109 here. For this one in particular, CH4, it's going to be actually 109.5, but 109 would be fine. And then SP, instead of doing this one, let's do this one. So it has a domain and a domain coming off of the carbon. So when you look at the hybridizations, you're looking at individual atoms, and it's always central atoms. Now, yeah, there's 2 carbons there, so there's, I guess, 2 central atoms, but they're going to have the exact same look. So 2 domains is always going to give you a 180. Okay, so you have to know SP, SP2, and SP3. There's some people that believe there's other valence hybridizations, but there's other people out there that disagree. So if you look and you find any other hybridizations, and if you look on the internet, you'll find some, or even in your textbook, some people consider that there might be some different hybridizations that deal with these, but there is a little disagreement between some parties. So right now we're leaving those out of the AP Chem curriculum. Okay, and then the other little type of vocab are sigma and pi bonds. And when you take college chemistry classes, you'll get a little more detail, actually a lot more detail than you are going to get in this class about them. But let's go back and look at maybe ethine. Okay, so I think we said 2 domains. It was sp hybridization, but we can also define all these different bonds. So every time there's a connection between atoms, we're going to call that a sigma bond. So there are 3 sigma bonds in ethine. But what we did not account for is there was a triple bond here. So we didn't account for those 2 other overlapping sets of orbitals that have electrons associated with them. So those 2 are called pi bonds. If you would have a molecule such as ethene, let's count these up. 1, 2, 3, 4, 5. 5 sigma bonds. And you could write out words instead of the symbols. And then we did not account for that spot right there. So there is 1 pi bond. I think at the end of the day, this is not a difficult concept as far as what we're doing in class. You just have to count these up. But it's not going to reflect very much on the test. I would say on the AP test, you might get 1 question And on the Unit 2 test, you might get one question on sigma and pi bonds. So this is the type of question you would get. Can you tell us the hybridization, and can you tell us the sigma and pi? And by the way, hybridization is always about the central atom. Okay, so you know what? We haven't done this one before. So it has one carbon. We don't have to name this, but if we did, it's meth. And then it ends in an OH, and that's an alcohol. So the molecule is methanol. So what would methanol look like? It's going to look like this. Central atoms, I know that looks like you could kind of say the oxygen might be the central atom, but the carbons are always the central atom. And what would be the hybridization there? Well, it looks like it has 4 connections, 4 domains. So that would be sp3 hybridization. We don't have to do the bond angles, but let's do the bond angles. Since it has sp3, those bond angles are in the 109 range. Sometimes you could say 109.5. That's either way is just as fine. And then how many sigmas and pi's? Well, it looks like they're all single bonded, so each of those count as a sigma. So I think I counted up 5. So it has 5 sigmas, and there are no pi's because there's no double or triple bonds there. And that's it.